behind it is actually your second law. Okay? So as far as the first statement is concerned, you have your entropy, and at the end of the class, this is where we define, right? The symbol for entropy is S, the unit is kilojoule per kilogram K. Okay? So simple as so the definition is this, right? Okay, actually on the sideline I can give it to you. Delta S change in entropy is actually change in heat transfer over absolute temperature. Right, so now mathematically it becomes like this, the integral. Right, so you like this is the definition of our entropy. So the change in entropy will be given by the integral of the heat transfer divided by the absolute temperature. Okay, this is an important formula to enable you to find the entropy. Why entropy now? Because entropy is the key property inside your second law of thermodynamics. Just like first law of thermodynamics, what do we have? Change in internal energy. Correct now? Our first law of thermodynamics, Q minus W is equal to delta U. First law gives rise to this concept called internal energy. Second law will involve the property called entropy. The definition is there. Okay, now having said all this, you notice that, okay, you can throw this away if you want, alright. Okay, but then, I mean, the reason I give it to you because so that you can understand it. Okay, but as far as application is concerned, okay, you hardly use it. I mean, you know it as a fact. Okay, now, in order to understand this second law of thermodynamics for our purpose, right, we have our what? We have our Kelvin and Planck statement. Now, this one, I think, this is something that you would want to remember. Correct or because this is something that you can easily follow, you can reason out, you can explain, you can argue. And then when we study our heat engine, alright, this principle of this second law will be behind our concept, right? We are our what is called theory. Okay. Now so what is this now? So just recap all we have done in the last class. So this is a quick recap. You have your Kelvin-Planck statement. Okay. It is impossible to construct a device which will operate in a cycle, extract it from the reservoir, and do equivalent amount of work. Okay. Okay. So now, if I want to now represent that statement with a diagram, alright, this is what happens. Okay, a cycle, single reservoir, taking heat, change it all to work. So now I change all the heat to work, W equal Q. First law never say cannot. Correct or not? In the last class, I used number to show you. I take in 10, I produce 10. But of course, if I take in 10, I produce 20, cannot because you cannot get something for nothing. Correct or not? You cannot create something from nothing. So if I take in 10, I create 10 or convert it to 10. First law never say. But second law say cannot. Alright, that's the beauty of it. So in other words, the arrangement is impossible. Can you see now? To make it possible, you will need to have what? You will need to have a co-reservoir. So what it means is this, right? You will require two reservoirs to run a heat engine. While one reservoir, the heat reservoir, is where the heat will enter the system. The co-reservoir is where the heat will be rejected. Right? So the difference between the heat supplied and the heat rejected will give you the work done. So you notice first and second law combine together to give you this. So this is workable. Okay? So that's all. Very simple. So that's why I say this second law when applied to heat engine, you can actually follow. You can have steps to follow. Correct? Now each step at a time you can reason out. Okay? So now the other one is your Clausius statement. Alright? The Clausius statement, it is impossible to construct a device that operating in a cycle produce no effect other than the transfer of heat from a cooler body to a hotter body. So a situation like that, you want to heat now to flow from a cooler body to a hotter body by making a device work like that, this is impossible. Why is it impossible? Because this arrangement, right, is actually represented like this. Because heat can only flow from hot body to cold body. Now you want to make heat flow from cold body to hot body. This is an impossibility. Okay? Okay, now if it is impossible, how come we have air conditioner, aircon? So now, in order for the system to work, you must put it work here. Can you see now the difference? This is impossible. Why? Because there's nothing here missing. So this one understand what? The effect. Okay, you have to introduce work. So when work is introduced, so this heat will be drawn out, work is introduced, so Q1 will be Q2 plus Q plus W in. So this comes from your first law, conservation. Correct? So W in and Q2 add up to give you Q1, both out. Okay, now this is possible. This is impossible because there is no work down here. Alright? Can you see now? So you can see now with the diagram, you can explain, you can reason out, go by step, make it more exciting, interesting. Whereas all these just statement only, all you have to do is just recite it and full stop, finish. Where do you go from there? Correct or not? So that's why now for your case, right? Keep this definition in your database. This one, extra, okay? I mean, these are side dishes, alright? This one is the main menu, okay? The main menu, okay? Now, so it is done, huh? Okay. Alright, now. Okay, now, so this one is, okay, now, 10 minutes gone by. The first 10 minutes now, I just actually recap what we have discussed previously. Okay, previously, so to get you to warm up, okay, warm up, okay. Alright, now, because now I have actually, right, still on the topic of second law of thermodynamics, okay. Okay, now, so very quickly, I go through this word first, very quickly. Okay, here, I'm going to show you something, you just tell me. The simple demonstration highlight a very important concept in your second law of thermodynamics, the result. And then, right, we also, okay, make use of it, alright, make use of it, okay. So here you go, alright. Can you see now? I have two pieces of paper. Okay, two pieces of paper, So I label it A, label it B. Okay? Okay? So now I'm going to do something to the paper without you watching, right? Then you tell me what happened. Okay? Okay? I've done something to this piece of paper. Hope you can't see, otherwise everything is right. Cannot see, right? You didn't know what I've done to it, right? All of you accept that, because I've hidden it. You cannot see what I've done to the paper. Okay? So now, I show you now. Let's see whether those with sharp eyesight weren't able to tell me. Okay? What have I done to A now? Apparently nothing, correct? What have I done to B now? What have I done to B? Huh? What happened to B now? Right? You observe carefully now, right? B now has become torn, alright? Correct now? So for B, I torn it. For A, apparently to you, I have not done anything, but you are wrong, right? I have done something to A also. Okay? So the question is, how come? Right, there's something I've done to A, you cannot tell. But there's something I've done for B, you can tell. What happened to B now is, you see, I have torn it. Okay? Alright? So actually A, you know what happened? I rotate it one round, alright? Okay? And then I rotate it back to my original position. Okay? So can you see now? So you notice, one action is what we call reversible. That is A. The other one, that is B, is irreversible. I cannot undo it and give you, I cannot tear it after that, return to the original state. Alright? You follow now? Now this one is to highlight what we call reversibility. Alright? A is reversible. B is irreversible and in fact highly irreversible. There are some instances where the reversibility is very small. Okay? Alright, so if you ignore, it can be considered as reversible. That means that event can go forward and backward. Okay? Like A, of course, highly reversible because you cannot detect from the beginning state. But for B, alright, it's highly irreversible. But there are some processes which apparently you have brought it to the original state, but if you consider carefully, it is not totally the original state. But you want to ignore the differences, you can easily treat it to be the same. Okay, what I'm referring to is this one. Alright, take a look at it. Okay, here the door. I open the door and then I close it. Okay, so when you see this closed door before and after, can you detect the opening now? You cannot. Correct or not? It's the same thing, right? Then I show you this one. Okay, I hide it, I open it and I close it. I show you the last part. You will never realize that I open it and close it. Alright, so to you it is reversible, highly reversible, correct? Or because I can go forward and backward. But if you examine closely, alright, starting off is here. If I open it and I close it, this one is different from the beginning, you know. In what way? The hinges become warmer. Do you follow now? But if I ignore these small changes, it is reversible. Correct or not? So that means to say this is not totally reversible, but highly reversible. Highly reversible. That means that if I ignore the changes, I can consider it to go back to the same state. But you know that it is not true because before that, the hinges has a certain temperature. So if I open and close it, the temperature will change. So I did not bring it back to the original state. But if I ignore these small differences, I consider it reversible. So in other words, reversibility has different degree. Alright? This one highly reversible. This one is highly irreversible. So in between the two of them, there are events, okay, which have different degree of reversibility. Just like the door, right? Okay, correct now? Alright? I open one time, maybe no, but if I open 1,000 times, maybe the whole process becomes irreversible already. I mean, you can detect the irreversibility. So in conclusion, from this example, this is what happened. Okay. This is something you must take down, but note. For a process to be reversible, right, your change in entropy, right, is equal to 0. That means to say delta S is equal to 0. This is reversible. Okay? For all the discussion, that is the conclusion, right? If the change in entropy is 0, it is reversible. And we call this one isentropic process. So take note, because if you encounter the word isentropic, you know what it means. No change in entropy. S1 or S1 equal S2. Okay? S1 equal S2. S1 entropy beginning equal to entropy at the end. No change in entropy or change in entropy is 0, that process becomes reversible. Alright, and we call it isentropic. Isentropic means entropy remains the same. Alright, S1 equal S2. Okay, so for delta S, which is not equal to 0, the process becomes irreversible. Okay, so the degree of irreversibility will depend on this change. If a change in entropy is very huge, highly irreversible. If a change in entropy is very tiny, alright, is a high degree of reversibility. But of course, alright, you know that in theory it is reversible, but I mean if the change is very small, you can consider it to be 0, you can treat it as reversible. Okay? You follow now? Okay, so that is the important point out of this discussion. Okay, reversibility, irreversibility, based on your entropy. So reversible process is isentropic, no change in entropy, delta N is 0. Right? So taking this term, isentropic, okay? So what is reversible? Reversible means it can go forward and then backward without change in property. Okay? I've shown here, right? If I tear a piece of paper, it goes forward, it cannot go back already. I cannot reproduce. Right? So it goes highly irreversible. Right? So in other words, if I tear the paper, the final entropy, right, will be much greater than the initial entropy. Okay? Okay. Now of course you will ask me how do you measure entropy and so on, okay? Okay, later on we'll do that. Okay? Okay, maybe we can do this one. After that we will use, I got something for you to show you there later on. We wrap it up by looking at the video. Okay? Alright. To answer the question, how do you find the change in entropy? For simple system we can. Okay? For simple system, like shown there, alright? For simple system we can find the change in entropy. And now during your reading, right, you must concentrate on this. This is what I want to show you. Okay? Your change in entropy, the formula is here. Okay? You see, I use here change in entropy. Can you see now? You see what I've given you. Now apply this formula now to simple processes. That simple processes are these constant pressure, constant volume, constant temperature, polytropic, adiabatic. The same 5 processes we considered in the past. Okay? Alright, now just to summarize. Okay? Here. Now, do I use your textbook or do I use one? Now maybe I think I will use your textbook. Okay? So that it's easy for you. Okay? So in the last class, I'm sure you have seen this. I think we have gone through all this also, although in a very fast pace, but still we have gone through it. Okay? Alright, now so last week we went through now equation of state, change in internal energy, work done, heat transfer. Okay? So we notice we have a final row which is now change in entropy. So for the 5 processes, constant pressure, constant volume, constant temperature, polytropic, adiabatic, what are the change in entropy? So in other words, how do you get all these formulas? Like I say, this is important, right? You ask for change in entropy, use the formula, that's all. Able to evaluate, right? But now, very quickly, we go and see how the formulas are obtained. Right? So like for example, this one, constant volume process. Okay, right? So now, by making use of this relationship concerning constant what I call volume process. Okay, can you see now? Alright, so a bit of mathematics involved. Okay, so now if you look at this, okay, never mind. I will just go through this first instead of switching here and there. This is for constant volume process. So now what should go into your mind will be this, alright. First, you have this formula. Where is it? This formula, right? Okay, and then if you look at the constant volume process governed by mCV times T, alright? Correct or not? Okay? Heat transfer. Okay? I'm not going to go into detail, alright, because I think this is not our main concern. I'm just showing you how to get there, that's all. With this one, you have to sit down and consider carefully. Okay? So if I do the integration, this is what I get. So now, to answer the question, now I have a formula to find the change in entropy for A1. Constant volume process. Okay? Now, so I can also have, right, very quickly, right, here. Constant temperature process, constant pressure process. Okay? So now, you just go through now the process, right? The constant pressure process or related pressure formula will be this because delta Q is MC T delta T, right? Then you evaluate to get the formula. Constant temperature, same thing, right? Okay? Based on your constant temperature process or heat transfer. Okay? So now this part all this you must know, able to follow, right? Because heat transfer for constant pressure process is this formula. Heat transfer for constant temperature process is this formula. Uncertain, don't know where to get it, go back to the table, you will find it. Okay, so I'm not going to go through again now. I'm showing you the step. Right? All these, right, because we have considered in the past, correct, a constant temperature process, what is the heat transfer? So if you cannot recall down here, right, never mind, you go to the table, look for it, it will be there. Okay, right, like I said, this one you have to do it in your own quiet breathing now. Okay, alright, so now if I do the integration, now so the step from here to here is mathematics. Okay, you know the mathematics, you will understand or you agree. If you don't know the mathematics, you have to accept it. Okay, alright, that's why the natural log comes in, huh? Alright, natural log because of the integration. Natural log. Alright, okay, now, so that is our constant pressure, constant temperature. Next one will be polytropic. Now, in a way, if you go through this one, alright, it will be beneficial because you will be pressurized to answer the question, what is the heat transfer, right? Alright, for our polytropic process, the heat transfer is given by this one. Okay? It's given by this. So you don't know the formula involved, you go back to the table, that's not the table I show you, you will find it there, right? Okay? You will find it there, here. Okay, down here. You don't believe, you look at polytropic process, change in heat transfer, right? Over here. Alright, polytropic process. The heat transfer will be here. Okay, heat transfer will be here. So now if I break it up, I get the change in internal energy and the work done. Can you see now, right? Down here, it's the same, I'm changing that. So now, of course, I have to use the correct formula. So now, doing all this, you find the change in entropy is given by this. Okay? Alright? Okay. Now, this is polytropic. You know, these are given in terms of what? Alright? Here. Alright? Natural log again, because of the integration. Okay? Now, finally, we have adiabatic. Right. So now, the beautiful thing about adiabatic process is this. Adiabatic process, Q is 0. So if this is 0, right, the change in entropy is 0. Can you see now? Okay. So that's why your adiabatic process is actually reversible. Can you see now? Change in entropy for an adiabatic process is 0. So that's why it's reversible. So that's why we call reversible adiabatic process as an isentropic process. Okay, take it in because this is a very important fact. Alright, reversible adiabatic will be isentropic. Change in internal, change in entropy will be 0. Okay, so these aspects and so on, you have to take it in. So at the end of the day, how they get the formula, you don't bother. Okay, so what you can do now is, very quickly, you just look at it. Okay. Oh, you break it here. Okay. Okay, I'm taking it in and now here. Okay. Alright, change in internal energy, adiabatic 0. Okay. This one, polytropic is here. Okay. Yeah. So with your textbook, you can see now in this one, the formula is this one. So in other words, they post it over there. Okay. Alright. Okay, that's confirm. I think it should be there now. Correct, 1 to 1. So the same thing for the others, alright? Okay. Alright, okay, let's try this one. Constant pressure process. Where is my constant pressure process? First one. Constant pressure, FCP log T2 minus T1. Can I have it here? Raise here. MCT log T2 over T1. It's the same now, right? You can take my word for it now, right? You can go back and check. So what the conclusion is this, alright? You have the textbook, the derivation, the final result, they put it into the table. Okay, so if you are ever asked to find change in entropy, use the table, that is the formula. Okay, I mean this is how you should approach the situation, alright? Okay. So I reckon the first reading of the textbook will be important, like you know where it comes from, right? If you cannot understand it, just let it go, but the formula you must know how to use. Okay, alright now. So that will be our change in entropy, huh? Okay, alright now. So having done that, okay, I have here about 5 minutes only, alright, so you just go through it. No figure, nothing. Okay. I think this part is the difficult part, because when you read it, it's very hard to interpret it. But you can always go to the YouTube, and then you can find, pick it up. Alright. Okay. What I'm trying to say is, right, it's useful to go through this one, because it represents our fundamental. Okay. This one, to read this and to follow the diagram, very difficult. I can understand that. So that's why this one you have to sit down and then consider it carefully. Alright? So don't worry, we are interested in the overall picture, alright? Okay? Get a piece of fact down there, some fact down there, and then you know when you are reading in future, you know what to go for, alright? Right? The diagram behind familiar, but just now we join was vertical, now on the side is the same. Right? The hot one is on the left, the cold one is on the right, whereas ours is the top and bottom. Did you see if and only if? Alright, that means to say the effect. Okay? So the video is to summarize what we discussed, correct? Alright? Okay? Just a summary lah. If you are keen and so find out more, go Yahoo and do it. Alright? I'm sorry, this is your YouTube, you can find it there. Okay? So now for our discussion, okay, you know this three term was mentioned, So heat and work, no problem. Our first law we talk about it. Heat engine, when we define our second law, we also discuss what is it. Now, Carnot cycle. Okay. Now, Carnot cycle is very important in the sense that it is the cycle that we use to compare. Use to use as a reference, alright, our Carnot cycle. Okay, now so I'm going to go through now the essential of a Carnot cycle. Okay, because it represents a point of reference, right? So it is a simple cycle. So that cycle, Carnot cycle, is the wood producing cycle. Okay, alright. Okay. So now we're going to look at it on a TV diagram and then a TS diagram. Both are representing Carnot cycle. Okay. Alright. Okay. Now so the Carnot cycle on a TV diagram is like this. Right. The device that performs this cycle is shown just now. You see your piston and your cylinder arrangement. Okay. Alright. Okay. So now first get 1 to 2. Okay, then 2 to 3. 3 to 4. And then 4 to 1. Okay? So this is the Carnot cycle. Right? So 1 to 2 is the isothermal process, constant temperature process. Okay? 2 to 3 adiabatic, reversible adiabatic. So that is to say isentropic. Okay. The Carnot cycle on a PV diagram is shown here. It is made up of 4 processes. So the 4 processes are listed here. 1 to 2 isothermal, same temperature. 2 to 3 reversible adiabatic, isentropic. Okay. Reversible adiabatic, right? We have equation and so on. Okay. And then 3 to 4, right? Isothermal also. Now, okay. One we distinguish. This is isothermal compression. Okay. No, sorry. Okay, let's try again. Okay. 1 to 2, let me see. 1 to 2 is isothermal compression. Okay, isothermal is still there. There are so many dyes down there.
Isentropic.
Isothermal is still correct. Alright, but this one is heating. Okay. 2 to 3 is reversible adiabatic. Alright, this one is compression. Okay. 3 to 4, again is isothermal. Alright, so this is cooling. And then 4 to 1. Maybe they are all there, right? Maybe you take out your book and so on, maybe you can help me to check. Okay? Alright? Alright, this one will be reversible adiabatic expansion. Okay? Okay, on my part, I also do a bit of checking down here. Alright? It's very easy to get confused over here because those lines are essentially. Okay, now the problem is that I do 1 and 2 different from your book. Okay? Alright? So now, you also have to do a bit of, can you be doing it also, doesn't matter, you stay here, take it as an exercise to track, see whether it is correct or not. Alright. Your 1 to 2 isentropic expansion. Okay. Now, if you look at your textbook, okay, you don't have a PV diagram. So now how are you going to check now? So it doesn't matter, you look at this one first. Alright, you have isentropic expansion. This one, reversible adiabatic. Just now we have discussed, right? Reversible adiabatic is isentropic, no change. Okay, so now, reversible adiabatic, this is isentropic. Okay, so isentropic, compression, okay, I think that's a mistake now. Right here. This one is cooling. I got the cooling and heating reverse. What to do? First time is correct. Isothermal cooling. This one is isothermal cooling. It can be established, right? So I think the only thing doesn't matter if you get it right, right? So at the same time, you take this opportunity to go through and then check, all right? Because in your textbook, you don't have this PV diagram, okay? And then, right, that's why we try to get it correct first, then we go to this, then you can understand. Isothermal cooling 1 to 2, right? Okay, so 2 to 3 reversible adiabatic, reversible compression. Okay, to 3 to 4 isothermal heating. Okay, 4 to 1 reversible adiabatic expansion. This is isentropic. Okay. Now if you try to figure out, you're getting some work done here, okay, so let it be, because now we're going to tell you. Okay. So once it is done, now the thing is that, okay, alright, your book 1, 2 is different from mine, okay. So what I can do now, this time I change it for you, what do I do now? How do I change? One isothermal cooling. Two to 3. Isothermal cooling. Isothermal rejection. Two to 3. Isothermal rejection is 2 to 3. Isentropic compression. Isentropic compression 3 to 4. Okay. Isothermal heating is the 4 to 1. Okay? So now my 1 is my 2, my 2 is my 3, okay, my 3 is my 4, so this is 1. Okay? Alright, so let's establish that. Okay, let's hope that we get it right, otherwise we go through again. Okay? Alright, where are you now? Isothermal cooling 2 to 3. Okay, on this temperature 2 to 3. Isothermal same temperature, so 2 to 3 is here. Okay, then after that, reversible adiabatic compression, isentropic. So isentropic 3S. S is isentropic, no change in entropy. So now compression it goes this way. Okay, 3 to 4. Then isothermal heating, isothermal constant temperature, so 4 to 1. Okay, and then finally 1 to 2. Isentropic expansion. So isentropic is here, vertical line, this is expansion. Okay, bingo, correct? So no mistake now. So because I started off arbitrarily using a number, okay. So now you will be consistent with your textbook. Because the textbook show you this only. Okay, so now I'm showing you this one. The reason the confusion comes in because I use a different point. Okay, so that's why I call it okay. So in other words, PV diagram, TS diagram for Carnot cycle, they look like this. So the preferred diagram to look at will be TS. Why? Because it is a rectangle. regular. But this one, both are slow. That's why even when I try to put in the process, it's a bit confusing. It's not so easy to identify the graded process. Whereas this one is easy. You know why? This is temperature. So now you have two isothermal process, horizontal line. And then you have two isentropic process because entropy is here. So two vertical line and then two horizontal line. So your Carnot cycle on a TS diagram is a rectangle. Okay, so that's why your book only carries this. Easy. Alright, now so for our case here, so correspondingly 1 to 2 is our one expansion. Okay, so 1 to 2 is our expansion. Okay, so on a PV diagram it will follow this. Right, so 2 to 3 isothermal cooling. Right, so when you cool the process, right, you will follow your isothermal process. Okay, and 3 to 4 reversible adiabatic, 3 to 4. Right, so this is adiabatic compression. So on the PV diagram, right, adiabatic compression is here. Isothermal heat rejection is here. Okay, alright. Alright. Now, I think you also agree that this diagram is more difficult to decipher. Okay, alright. Okay, so I'm giving you a bit of extra here, so it turned out a bit confusing. But I think if you want to find out more, understand more, this should be it. So I think what I have is here, right? This one, right? Right? This one is expansion. This one is compression. Okay? This one is 2 to 3 is what? Cooling, right? Okay, this one is heating. Okay? Alright? This is easy to sketch. Alright, so but this one, confusion. The done I have done, alright, confusion. But it can be established, or you can do that. Alright. Always the case, every time I come to this point, I always got mixed up. Alright, always got mixed up. Okay? Alright. So in other words, if you ever want to sketch this diagram, right, you must know the process and then how it slopes, right? Okay? No, wrong. 1 to 2 expansion, I got it wrong. Okay? This is expansion, 1 to 2 is expansion, I got it wrong. P to 4 is compression, this is compression. Then this is expansion.